All right, hello and welcome to Space Drafts number 116. My name is Nick. I am a graduate student at the University of Arizona in the Department of Astronomy. For all of you here, welcome. For those of you who are new here, a very special welcome to you. This is Space Drafts, Tucson's version of Astronomy on Tap. And if you're not familiar with Astronomy on Tap, it is a worldwide network of events that are designed to bring astronomy to you, the general public, in bars and pubs around the world. So if you are in Tucson visiting tonight, or if you're joining us online, there are possibly AOT Astronomy on Tap events near you. So go check out their website. They are there. You can just search them on Google, and there are events all over. But this is Tucson's version. Our show tonight consists of two 25-ish minute talks. We'll have some time for questions with our two wonderful speakers once their talks are over. We will have a 20-minute intermission between those talks, which is your opportunity to go and refresh your drinks, have a little chat, and we'll come back to the second talk afterwards. Let's see. We also have trivia questions in each of these talks tonight. That is your opportunity to win a little piece of our merch. Speaking of our merch, back at that table over there, we have Soleil. We have some merch available for sale. We can only accept cash, unfortunately. We do not accept credit cards or any other payment. If you do not have your cash tonight, come back next month and get some merch. The other thing I have to mention tonight is floating around, especially during intermission, we have some volunteers from the organization called SACASA, the Southern Arizona Center Against Sexual Assault. They are an organization that supports sexual assault survivors. 20% of proceeds from sales here on Z Street tonight go towards supporting SACASA and their work. There are also raffle tickets available for sale. If you want to learn more, there will be volunteers floating around Z Street tonight. So go ask them, I'm not the expert. But yes, with that, we shall begin our show with our first talk. Here to give you a wonderful introduction about the colorful world of spectroscopy, please give a warm welcome to Lunar and Planetary Laboratory graduate student, Cole Meyer.
Thank you, everybody. Okay, can we hear? Nice, awesome. Well, yeah, I'm Cole Meyer. I'm a second-year PhD student in the Lunar and Planetary Laboratory at the University of Arizona here in Tucson. And today I'm going to tell you about one of my favorite topics of all time, which is color in space. My day-to-day job involves building instruments that can measure color of astronomical objects and using observations from those instruments in order to infer stuff about the objects that we're observing. So today I'm going to tell you everything I possibly can about color in space. Certainly I'm still going to miss some things, so if you come up with any questions throughout the talk, please vigorously write them down in your notes app and we can talk about them during the Q&A or during the intermission. And the last thing I thought I would mention is that you'll see the amazing Space Drafts team passing out some little rainbow cardboard pieces. Please grab one or share with a friend. They will be used for a demo a little bit later in the talk. So with that, I wanted to spend the first couple of minutes with you all talking about and appreciating some of the most beautiful images that have ever been taken over the last few decades of space. So let's get into it. So this is an image of an object called the Veil Nebula taken by the Hubble Space Telescope. Now this is a beautiful image, lots of detail here, a lot of information contained within the image. You can see that there appears to be some kind of bright emission spanning from corner to corner, maybe it's a gas. You can see some kind of diffuse gas in the background as well as stars. But what happens when I add the color back into this image? Wow, look at how much information is being conveyed using color in this image. I mean, for one, look at the filament. You can see that there are different qualities of the gas. Maybe it's temperature, maybe it's composition. You don't really know without a caption on this image here, but the point is that the color is being used to convey information about the object that you're looking at. So let's look at another one. This one is NGC 602, located in the Small Magellanic Cloud. This image was taken by the James Webb Space Telescope. Again, beautiful image, a lot of information here. You can see there appears to be a really large object, sort of in the middle, maybe some kind of diffuse gas in the middle, enclosed by a sharp, jagged shell of gas. You can also see stars and even galaxies in this image in the background. But what happens when I add the color back in? Wow. So much information is being conveyed here. So my point in showing you these two images is to tell you that color can be used in a very powerful way in these images beyond just creating a beautiful image. It can be used to convey stuff about the physical processes occurring within these objects, the motion, the kinematics of the objects, and also the environmental conditions of the objects. So before we get into all of those things, let's ask ourselves a deep question, which is, what is color? And to that deep question, I'm going to give you a not so deep answer, which is that really, color is a psychological phenomenon. It's not really real. Color is the brain's way of making sense of electromagnetic radiation received by the eye. So this is a diagram of an eyeball, and what I want you to look at here is the cones and rods lining the back of the eye. These are called photoreceptors, or receivers of light. They're detectors for your eye. And the important part for the purpose of this talk is that these different types of cones and rods respond to different colors at different amounts. So for example, the S cones respond very well to blue light, whereas the L cones respond very well to red light. So if your S cones receive a whole bunch of light and therefore produce a whole bunch of electrical signal for your brain, whereas the L cones don't receive so much light and therefore don't produce as much signal, your brain is going to know, okay, whatever I'm looking at here is mostly blue and not so red. And that's how your brain goes about reconstructing the actual color that you're seeing. So this is an example of this principle in action. This is my cat, Sophie. She's a little bit funky in this image, but very cute nonetheless. So the full color image, of course, is in the top left, and all of the other three panels are color channels, red, green, and blue. And so if you would add these three panels together in equal proportions, you would be able to perfectly reconstruct the full color image on the top left. This is the same principle occurring with cones and rods in your eye and the way that your brain makes sense of the inputs from those cones and rods. So there is a problem here, which is that if you remember back to the response curves that I showed you, they really only have a response in visible spectra over the visible wavelength range. Not any of these other wavelengths: gamma rays, X-rays, ultraviolet, infrared, microwaves, radio waves, long radio waves. Your eyes cannot sense any of these wavelengths. And yet, astronomical objects and astronomical processes produce light at these wavelengths, at these colors. So the question becomes, what are we missing out on through all of these other colors, all of these other wavelengths of light, and how can we go about measuring them? So I described these three kind of buckets of stuff that can be represented with color. As anybody that is kind of familiar with the space sciences knows, there's an innumerable number of things that are represented by color in space. These are just kind of my ways of like decomposing all of those things. So the first bucket is physical processes, also environmental conditions, so like temperature, composition, density, things like that. And finally, kinematics or motion. So for each of these buckets, I'm going to go through and give you one example of a way that color is used to represent it, and we'll go from there. So let's start with physical processes. So this is a beautiful image obtained by the James Webb Space Telescope of the Carina Nebula. Very famous. Hopefully everybody has already seen this one. But if it's your first time seeing it, congratulations. So what we're seeing here, in the very top, in the blue section, is the home of a bunch of really hot, bright, massive stars. And those stars are emitting harsh ultraviolet radiation into their environments, including into the gas in which they were once formed. And the orange, the red, the brown, that color on the bottom, that's the gas where it was formed to begin with. So this is molecular gas. It's very fragile, and it's not very, it can't withstand ultraviolet light that's being shined onto it from the nearby stars. So what you're seeing here is, in this boundary, is something of a battlefield between the harsh ultraviolet light from the stars and the very fragile molecules in the very bottom. So in this image, color is not only being used to represent to us mere humans what's going on, but also the actual types of gas emit different colors. So when James Webb points at this thing, it will actually measure different things for the different types of gas. And so you're learning from the data what is actually there, and also using color in a slightly different way to represent it to us mere humans that can't see at infrared wavelengths. Here's another bucket, which is environmental conditions. So this image is taken by the Hubble Space Telescope, and it's of an object called the Jewel Box Cluster. So what I want you to pay attention to in this image is the color of the stars. So you see in the very middle, there are a bunch of obvious kind of really bright blue stars. But if you look a little bit more carefully towards the corners in these clouds, you'll see that there's also a bunch of red stars. So what's going on here? My understanding of this situation, I'm not a stellar astrophysicist, but this is my take. All of these stars were born roughly at the same time, about 14 million years ago, in the same cluster, in the same parcel of gas. Over time, the more massive of those stars depleted their fuel more quickly. They aged more quickly and they turned color. So all of the stars that you see here that are red were once born to be much more massive than the now blue stars. So not only is color telling us about the temperature of the star, it's also telling us about like the early initial conditions of star formation in the cloud. So incredibly powerful stuff we're talking about here. And last but not least, kinematics or motion. So hopefully everybody is familiar with the idea that when an ambulance is blaring its siren and it's moving towards you, the sound that it emits is a little bit higher pitched. But when it moves away from you, it's a little bit lower pitched. This is the Doppler effect. So what's going on under the hood here is that as the ambulance emits a sound wave towards you, and the ambulance is moving towards you also, the sound wave is compressed. The wavelength is shortened, and the sound is blue shifted. When the ambulance moves away from you, it extends the sound wave, the wavelength increases, and the sound is red shifted. So the same exact principle applies to light. When something is emitting light and moving towards you, that light is made slightly more blue, and when the thing is moving away from you, the light is made slightly more red. So let's turn back to what I'm showing here. So what you're seeing here in the orange-red is a so-called protostellar disk, or a pre-star disk, okay? This whole thing is rotating around, and it's slowly falling inwards towards a really bright, hot ball of gas and dust in the middle called a protostar. And it's feeding that protostar with the gas and dust, but all of the gas and dust rotating inwards is not eaten up. Some of it needs somewhere else to go. And so the place that it goes is into these high velocity jets, shown in green there, okay? So one might imagine that because the disk is rotating, maybe the jet would be rotating too. How could you figure this out? Well, let's look at the data on the right side. So this is showing the amount of red shift and blue shift, the change in color. What do we remember from before? The blue on the top right is blue shifted, like the ambulance moving towards us. So that part of the image is moving towards us. The red is red shifted. The ambulance is moving away from us. That part of the object is moving away from us. So we've deduced, just by looking at the color of this image, that this thing is spinning. The whole thing is spinning. And we've deduced the direction of rotation and how fast it's rotating, all from just looking at the shift in color. So this, like I said, these are just three very specific examples of ways that color is used in space. There's many, many, many more. I would encourage you to turn to my colleagues dotting the entire audience right now and ask them for more examples. It's very interesting stuff. But my goal with this talk is just to convince you that color is very important and we want to measure it in space, okay? So then the next part that we want to turn to is, how do you actually measure the color? If we know that we want to measure it, how do you actually do that? So I'm going to kick it down the line a little bit further and tell you how they did it back in the day, and then later in the talk I'll tell you how we do it these days. So back in the day, late 1600s, Sir Isaac Newton was one of the first to show that if you shine white light into a glass prism, the light will disperse into different colors, as you can see in the image here. He wasn't actually the first, but he was the loudest, so that's how that usually goes. A little bit later, William Wollaston built a spectrometer. This is an instrument that can measure and record color, okay? And he pointed the thing at the sun, because the sun's really bright, and he found, okay, you see a rainbow like you would expect from a prism, but you also see some weird, like, dark lines in the rainbow. Very interesting. A couple of years later still, Joseph von Fraunhofer, 1815, invented a new optical component that I'll tell you about in a couple of slides, and he pointed his new spectrometer back at the sun, and he saw a very crisp view, which you can see in the bottom left there. So what you're seeing, again, a rainbow plus a bunch of dark lines. And this time he found over 750 of these dark lines, and he said, what the heck are these? And he labeled them A, B, C, D, E, F, G, H. So he really had no idea what these were, but he saw them very clearly. Okay, a couple of years later still. Actually, I want to tell you a fun fact. Because that whole spectrum is rectangular, and you see there's like dark lines in it, sometimes it's called barcode. So this is a solar barcode. Hence the title of my talk, The Universe's Barcode. There you go. A couple of years later still, John Herschel and William Talbot, they observed that if you would burn different types of metal salts, the flame that was produced had a color corresponding to the type of salt you were burning. Very interesting. A couple decades later, Kirchhoff and Bunsen discovered that this observation about flame spectroscopy extends much, much further. Really, any chemical that you could possibly test has its own color signature, its own spectral signature. In other words, it produces its own set of dark lines in the spectrum. Also, Kirchhoff, he was pretty cracked, he did a lot of stuff. He also formulated 3 fundamental laws of spectroscopy, which I won't really get into detail about, but generally it tries to understand, like, if I would look at a really hot source, it produces one type of spectrum. If I would look at a hot source plus a cool gas in front of it, it produces a little bit of a different spectrum. So the point is, we're kind of getting a better understanding of how this stuff is working. And finally, quantum mechanics was born in the 1900s. And it turns out that the way that molecules and atoms interact with light has deep, deep roots in quantum mechanics. So as soon as we started to understand what was going on under the hood with all of these atoms and molecules, we started to understand what spectroscopy, or the measure of color, actually is, what it's telling us, how it works, and we could make predictions and test our theories. So with that, trivia time. I was told to remind everybody to raise their hands after I read the question. So here's a question. Spectroscopy eventually allowed us to find new elements. Which gas was discovered in the sun's spectrum during a solar eclipse in 1868, years before it was found on Earth? I saw your hand right away.
Helium.
Helium. Correct. So if you happen to not know that answer from history and whatnot, you could, and you happen to know Greek, you actually could figure it out. Helium is named after the Greek word helios, which is sun in Greek. This whole element was named after the fact that it was discovered in the solar spectrum. So the way this kind of went down was they had looked at the solar spectrum and found all of those dark lines. And at the same time, other people, Kirchhoff and Bunsen, for example, were in the lab showing that different lines could be produced with different elements. So then they started identifying different elements from the solar spectrum, and one of them remained unidentified, and they called it helium because they had no idea what the heck it was. And it turns out to be actual helium as we know it today. Okay, so I mentioned that back in the day, Sir Isaac Newton had used a glass prism to disperse light into its colors. This was used for a while, and it's still really used today, but it's not always the most effective, so I'm going to tell you about an alternative to the prism. And it's not ideal for a couple of different reasons. One is that the color actually isn't dispersed very much. It's hard to identify or distinguish immediately adjacent colors from one another. Or in other words, the spectral resolution is hard to get high with instruments that incorporate prisms. So that was one challenge. The other challenge is that it's glass, and some wavelengths of light are just absorbed by glass. So if you want to look at the ultraviolet, for example, you just can't use a prism because all of your light will be absorbed. So those two facts kind of motivated the invention of this new optical component that I mentioned a little earlier, called a diffraction grating. So these diffraction gratings are amazing. It's basically a mirror, like a flat mirror, with a bunch of tiny little grooves ruled into it. So you can see in this case, it's like a sawtooth pattern. There's other patterns you can make. But when you shine white light onto this surface, some of it reflects, as you would expect from a normal flat mirror, but a bunch of the light disperses into color very well. So you can see, I've shown check marks on the bottom to show that this solves both of our problems. The color is dispersed very effectively, so you can achieve high spectral resolution instruments, and also you can apply mirror-like coatings to these things to make them efficient at a bunch of different wavelengths. Okay, so now for the fun. So hopefully everybody has a little piece of rainbow cardboard. Okay, does anybody have a guess for what they are? It's a diffraction grating. The slide says so. Okay, so these are a little bit different than the previous ones I described. These ones, the light diffracts after passing through them, as opposed to reflecting off of them. So if you would hold it up to a bright light, like these LEDs are really good for this, and you look directly at the light, you're probably still going to see the light. But if you look a little bit off to the side, you'll see these diffraction orders, this m equals -1 or m equals +1. So you're seeing the spectrum produced by the light. And if you look at different types of light, they're all going to have different spectra because they all work differently and they all have different filters on them. So I would encourage you, I won't be offended if you're doing this during my talk, but especially during the intermission, I would encourage you to walk around and try to find different colored lights, like the red lights in the back, You probably have to get right up next to them, but you can get really good pictures. So here's a cheat sheet for what you might be looking for. These images were taken a couple of space drafts ago because I was so excited about this activity. So those are the red lights that I mentioned. They're famous right there. So you can see that the spectrum is almost entirely red with a little bit of orange there. If you would look at a yellow light, I think that one's like back there by that horse thing or giraffe, whatever that thing is. You can see that there's interesting, a little bit of blue, a little bit of green, little red, but also a really bright streak of yellow, okay? So you see these other colors because presumably they are LEDs. So they create a certain color by combining a whole bunch of different colors as opposed to just shining yellow. Okay, and then if you would look back in my direction, hopefully you see something like this, really cool, just a bunch of different rainbows from all the lights around us. So play around with that a little bit, especially during the intermission. Okay, and with all of those things said, we now sort of have what we need in order to understand what a spectrograph actually is. I've mentioned this a couple of times. It's an instrument used to measure and record color or wavelength of light. Okay, so the general idea is this. You collect your light, you organize it in a way that's not really relevant for this talk, you pass it through the diffraction grating, just like the one that you guys have, maybe a little more expensive in reality. You capture all of the split colors with a lens and you focus them onto a detector. And hopefully you get something that looks like this onto your detector, which is intensity as you move across in one direction over your detector. And that represents color, the intensity of each color. Okay, so with all of that done, we kind of have what we need in order to understand what I actually do on a day-to-day basis. So let's talk about some of my research. Okay, so my research relies on the concept of high-resolution spectroscopy. So we mentioned a couple of slides ago that spectral resolution is the ability to distinguish immediately adjacent colors from one another. So if you have a high spectral resolution, you can really distinguish adjacent colors very well. But if you have a low resolution, you're gonna have a hard time doing that. So this is the solar spectrum that we've seen a couple of times here. This is what I might consider like a relatively high spectral resolution. You can see all the lines very clearly. They're very crisp. And right below it, this is a low spectral resolution. So you see that some of the lines just blur together. Some of them you can't see at all because they're just lost. They were too dim, too thin. And so it turns out that high resolution spectroscopy sort of unlocks another level of stuff that you can learn about what you're looking at through your telescope. So it's very powerful. The problem is that this is what they usually look like, at least very good ones. They are very large, very heavy, and maybe most importantly, they're very complex. Some of them are even in vacuum chamber, like it's crazy stuff. So my work tries to produce high resolution spectrographs that are small, they are not super heavy, and they are simple. Okay, so how do I actually do that? It sounds like witchcraft. This is how I actually achieve it. It's through a concept called spatial heterodyne spectroscopy, or SHS. It sounds complicated, it's really not. I'm not even gonna make you understand how it works. The key is that these things are able to achieve very high spectral resolution in a compact, lightweight package. And this makes them really good for flying in space, on spacecraft. So this is a schematic of what it looks like. Again, not gonna dwell on it. Happy to answer questions about it though. This is what your image on your detector looks like. It's a little different than what we were seeing before. And this is a model of what one actually looks like. So I'm planning to build this one in a couple of months here. But the thing that I want you to notice is this scale bar right here, which says 2 inches. So these things are quite small. The whole thing is like this big. So quite good for spacecraft compared to those other like bus size, very large spectrographs. And these things have their drawbacks that you have to consider, but they're also very good in many ways. Okay, so I mentioned that we want to fly them on spacecraft. The problem is that you need to convince NASA that you can actually do it, that your instruments are capable of doing the job that you say they can do. So the way that you demonstrate to them that they actually will work is that you fly them on a short duration sounding rocket. So these sounding rockets are small suborbital rockets, so they don't ever get up into orbit. They just get a couple hundred kilometers into the upper atmosphere. And you'll get a couple of minutes of observing time, which generally is good enough to demonstrate your instrument. Like I said, they're very good for proving technologies because they're cheap, they are low cost, I already said that. They are also low time commitment. So like I said, they only take a couple of minutes as opposed to a spacecraft that might be up in orbit for several years. So very good. And finally, they're a couple of stories tall. Like I said, they reach a couple hundred kilometers into the upper atmosphere, and ours generally launch from New Mexico at the White Sands Missile Range. Okay, so here's me in front of a payload in my laboratory. So this is just the middle section. If you wanted to add the pointy end and the flamey end, this is what it hypothetically would look like. It'd be very bad if that turned on. Okay, so last but not least, let me tell you about the actual mission that I'm working on. So the mission that we're actively working on is called SHIMCO. Okay, it has a nasty acronym. It stands for Spatial Heterodyne Interferometric, so hopefully that part sounds familiar, SHS, that's the instrument that we're building, Molecular Cloud Observer. Okay, so we're planning to fly a very capable SHS instrument on board this sounding rocket and use it to observe molecular clouds. This is where stars are born. We actually saw some molecular clouds in the images that I showed earlier in the talk, and we're trying to understand how these regions are created, and once the stars actually form, how do the stars destroy the birthplace that they formed in, the gas that surrounds them. So we are scheduled for launch about mid-2027, again from White Sands Missile Range. Hopefully everything goes according to plan so we can stick with the 2027 launch date. But yeah, so just to wrap up here, we discussed that color is a psychological phenomenon. It's not really real, it's sort of real, not really real. But at the same time, it can be used in a really powerful way to represent physical information in beautiful astronomical images that you might see. We also talked about how every color that is produced in space tells a story. It can be used to represent physical processes occurring in the objects you're looking at, environmental conditions, and also kinematics or motion in the objects you're looking at. And finally, I told you about these new SHS instruments and how capable they are of doing this high-resolution spectroscopy in a low cost. They are light, they are compact. And so I'm here to tell you that you don't need a billion-dollar instrument in order to do some really cool spectroscopy. You only need a few $100 million. So if anybody here is a private donor, let me know. And in the meantime, I'm happy to take any questions. Thank you.
Good question. One over there.
Yeah, so, thank you. Either way is good. So for SHS, first of all, it's so heterodyne. Does that mean you're mixing, like in circuits? Could you spend 30 seconds explaining how it works?
Yeah. Great question. Okay, let me go back to the diagram that I had. Okay, so this is the diagram. So generally, the way that this thing works is that the light still interacts with the diffraction grating. So the light is still split into colors. But this time, instead of measuring the colors directly, you're actually interfering the light with itself in a way that depends on color. So you get an interference pattern that looks like this, and the spacing of those lines depends on color. So then, I'm going to throw a word out just for the people that are familiar with it. You can take a Fourier transform and identify the frequencies present in the image, and therefore you can deduce what the spectrum looks like. Yeah.
Do you have to worry about thermal expansion or contraction in the diffraction grating?
The question was, do you have to worry about thermal expansion in the diffraction grating? The answer is that this type of instrument actually is very resilient to thermal expansion. Because the whole thing is like symmetric, if anything expands, both sides of the thing are going to expand, and they actually cancel out in most cases. So it's pretty resilient to thermal changes. That's a really good question.
Well, if there are no more questions, let's thank our speaker.
Thank you.
Last reader comes up. Thank you, Cole. With that, we shall go to intermission. Please head on in and refresh your drinks if you are so inclined. Come visit us at our merch table. There are volunteers from Sakasa around somewhere. We did tell them that 8 o'clock was intermission, so they'll be around if you're so inclined to support them. Don't forget to tip your bartenders. For our trivia winner, come visit us and get your little piece of merch. And with that, we will see you at 20 after 8. Don't forget to tip your bartender, and see you then. Alrighty, if you could please take your seats, we are going to come back to our second talk of the night. Just a reminder that food in Zerai closes at 8:30. The tacos close at 8:30. So if you want to get any tacos, hurry up and do that. Now, our second talk of the night from another Lunar and Planetary Laboratory graduate student. Please, here to introduce us to the early days of Martian evolution, please give a warm welcome to Ruby Fulford.
Good evening, everybody. Thanks for coming. I will be talking about Martian Mystery and Mayhem, exploring the enigmatic early evolution of the red planet. And my name is Ruby Fulford. So I'll start with a little bit about me. I'll start with a little bit about me. I'm a third-year graduate student at the Lunar and Planetary Laboratory. I earned my bachelor's degree in astronomy from Stewart Observatory back in 2022, so I've been in Tucson for a while. It's a great place to be a space scientist and a great place to look at the sky. I work with Professor Jeff Andrews Hanna, and I also spend summers working at the Smithsonian Air and Space Museum, and both here and in DC, I work on research that focuses on the early evolution of the planet Mars. Besides Mars, my research interests include astrobiology, which is the study of life beyond Earth and habitable environments beyond Earth, geophysics, icy moons in the outer solar system, and working with remote sensing data. A lot of my research is on the computer, which is the research I'll be talking about tonight, but I also like to get into the field when I can. Here's a picture of me doing some very important work in the field in California. When I'm not doing science, I like to get creative and do things like play guitar and write songs and make various types of art. So I included a picture of me rocking out. So I want to talk a bit about my journey to studying Mars and how I got interested in the earliest eras of our next door neighbor Mars. So when I was studying astronomy, I had to take some planetary science classes as electives, and I had to read some papers about the findings of the Curiosity rover, and I started reading about how Curiosity had found all this evidence of aqueously altered minerals, so rocks that have had contact with water, and how Curiosity had even found organic material, although it wasn't conclusively life, it was still really interesting. And that's when I started to really learn about how Mars was this totally different world in the past that had possibly lakes and rivers, maybe even an ocean, though that's up for debate. From there, I became really interested in ancient Mars and planetary science as a whole. And I realized that I wanted to veer in the planetary science direction once I got my astronomy degree. So after college, I took starting at the end of college, and also after college, I took a little detour and worked for the OSIRIS-REx mission, which, as I'm sure many of you are aware, was or is a mission that brought back a piece of the asteroid Bennu to Earth. And I spent a couple years building an imaging system that we used to take pictures of the sample when it got delivered to the lab in Houston. Here is a picture of me in the clean room with some of my colleagues with the instrument that we built. And that was a really amazing experience, and it was amazing seeing those super duper old space rocks. But I realized that I missed my old friend Mars, and I still had a lot of questions about Mars's past. So I decided that when I started grad school, I wanted to shift to early Mars research, and here I am now. So I'd like to welcome you all to the planet Mars. This is a beautiful image that was taken by the aforementioned Curiosity rover. This is inside an impact crater called Gale Crater, and it's looking at Mount Sharp, which is a mountain within that crater. And I love this image because this could be a picture. If you told me this was a picture of like Death Valley or somewhere like that, I would believe you. It's amazing. Currently, Mars has average surface temperatures below freezing. It's not suitable for liquid water. It's a very cold and desolate type of environment, although there are some polar caps that are comprised mostly of water ice, and there's also evidence for water ice elsewhere, so we know there's some water in the equation. Mars is a pretty small world. It's about half the diameter of Earth and 9 times less massive, so there's much lower gravity, which means it can have generally taller mountains, deeper valleys, larger landforms altogether because there's less gravity pulling things down. The atmosphere is very thin, at least presently, so the surface gets a ton of radiation. If you ever send people to Mars, they're going to have some serious radiation protection for that. And the lack of a thick atmosphere is also why it's hard for Mars to hold on to a warm climate. But like any planet, Mars has evolved and changed over time. And when we look at the geologic record of Mars, we can start to piece together a story about its past. This is an elevation map, a global elevation map of Mars. To be clear, the blue is not water, sadly. It's just the lowest elevation. I've highlighted a few of the key large geologic features on Mars to give you guys an idea of what goes on up there. Mars has been pummeled by a lot of impacts, as you can see by all of the craters on its surface. A couple huge notable ones are Hellas, which is this big one here, and Argyre, both performed by giant rocks smashing into Mars' surface. Here's Valles Marineris. It always makes me think of marinara sauce, but it's not marinara sauce. It is a giant canyon, about 4 times as long and 4 times as deep as the Grand Canyon. The thing's huge. It's still kind of a mystery how that formed, which is crazy, but it's thought to have formed due to the crust cracking as the freshly formed planet cooled. I also want to point out the Tharsis volcanic province. This is the biggest volcanic center on Mars. As far as we know, it's no longer very active, but it certainly was in the past because it's home to Olympus Mons, which is the largest volcano in the solar system, including all the volcanoes on Earth. And there's also these 3 huge volcanoes in a line, which are the Tharsis Montes. This will be important later. So by looking at the geologic record of Mars and by taking the chemical evidence that we can get from rovers, scientists have been able to put together a timeline of Mars's history. Just like Earth, Mars's history is split into geologic time periods that we use when we discuss the history of Mars. So about 4.5 billion years ago, and I want to specify that in this talk, GA means billion years. I think it stands for giga annum or something like that, but that's what that means. We got planet formation about 4.5 billion years ago. Yay. Mars condenses out of the protoplanetary disk somehow. That is not my area of expertise, though I'm sure there are some people here that could explain that a lot better. The first era of Martian history is the pre-Noachian. This is a very mysterious era. No one really knows what was going on because the geologic record from this era has been pretty much completely destroyed. There's really no part of the Martian surface that is that old. So she's mysterious, and that's something I want to explore later in my career. And then, around 4.06 billion years ago, we have the giant impact that forms the Hellas Basin. Now this impact throws out so much material that it kind of blankets the surface of Mars, and that's one of the reasons that we can't really see the pre-Noachian geologic record. It's all buried under Hellas ejecta, because, you know, when you make a basin that's 2,000 plus kilometers across, a lot was going to get kicked out of that. The Hellas impact usually is used to mark the beginning of the Noachian epoch, which is thought to be the wettest and perhaps warmest epoch of Martian history. When we look at Noachian terrain, we see a lot of evidence for water-driven erosion, including the formation of valley networks like this one that look a whole lot like dry riverbeds on Earth. There's also some evidence for volcanism during this time and tectonic activity. I'll explain this more later, but tectonic activity occurs when the surface of a planet is deformed and fractures and forms different types of landforms. After the Noachian, we have the Hesperian. This is a period defined by intense volcanic and tectonic activity, especially at the beginning of the Hesperian. Some valley networks continue to form in the beginning of the Hesperian, but the water activity kind of transitioned to huge floods that occurred every now and then that created huge outflow channels. The current period of Martian history is the Amazonian. It's also the longest. It has been going on for the past 3.5 billion years-ish. This is a period that's probably the least geologically active. It's defined by declining floods. There's some evidence of water happening in the Amazonian, but not as much as earlier epochs. There's some episodes of very young volcanism. There's also currently dust storms and weather events like that. There's even some evidence of glaciers in the Amazonian, which I think is cool. This is a image of a feature that's thought to be similar to a rock glacier, but it's on Mars. These later eras, though, are not my area of expertise. For my research and for this talk, I'm going to be focusing on the Noachian. So what do we know about the Noachian period and early Mars in general? From what we know about planetary evolution, we expect early Mars to have been more geologically active than Mars today. Planets tend to generate a lot more heat early in their evolution because you have leftover heat from the planet accreting out of the pre-solar nebula, and there's also a lot of radioactive elements within the crust and mantle of a young planet that will be generating heat, and as time goes on, less and less of the radioactive elements remain, so heat is generated at slower rates. But because of that, we expect a lot of volcanism to happen early in Martian history. We also expect there to have been a much different climate early in Martian history, including a thicker atmosphere, which could explain how early Mars is able to sustain liquid water. There's plenty of geologic evidence of a lot of activity at the end of the Noachian and the beginning of the Hesperian, which is about 3.74 to 3.7 billion years ago, as I touched on before. Evidence, which I also touched on before, includes the Tharsis volcanic province, which accumulated around the end of the Noachian and the early Hesperian, associated tectonic activity, and there's also lots of valley networks that formed in the late Noachian and early Hesperian. That was sort of the big boom of water activity on Mars. So it seems like we know a lot about the late Noachian, and the high rates of various types of activity in the late Noachian align with what we know about planetary evolution. But we don't know as much about the early Noachian. So the early Noachian spans the period from about 4.06 to 3.96 billion years ago, although the exact dates are definitely a topic of debate. The early solar system was a very violent place. There was a lot of rocks flying around, a lot of impacts happening, and so the old terrain on Mars is very heavily cratered. I have an example of heavily cratered early Noachian terrain here. They're all over the place. So as you could imagine, all of these craters and other types of degradation have kind of destroyed a lot of the record of what was going on early Noachian Mars. If we had like early Noachian volcanoes or early Noachian like rift valleys or valley networks, a lot of them would unfortunately be destroyed, so it's hard to investigate what those early conditions were. And we don't really know how those conditions compare to later conditions. What we do know is the early Noachian might have had high levels of volcanism and tectonism because, as I said before, planets generate way more heat early in their history, which can be expressed on the surface as volcanism. We also know that there was actually a lot of water-driven erosion. We don't see clearly formed valley networks from the early Noachian like we do in the late Noachian, those pristine river valleys that I showed, but we do see that Noachian craters are very heavily degraded. They look a lot different than fresh craters. This is a fresh crater. It's nice and sharp. It has this raised rim. It has a little central peak, whereas craters on early Noachian terrain look like this. They're flattened, they're full of deposition, and this shows us that some type of water erosion kind of destroyed these craters, there was probably a very arid climate during the early Noachian because we don't see valley networks, but it was an environment that could sustain liquid water, which is cool and very good for astrobiology purposes. So, before I get into my research, we're going to do a little trivia time. Please raise your hand if you have the answer. The question is, what was the name of the giant impact that marks the start of the Noachian period? Is it Argyre, Hellas, Oriental, or Big Boy? Anyone know? Yep? Yes, correct, as Hellas. It is not Big Boy, sadly. So my research focuses on figuring out what was going on in the early Noachian, because who knows? So in order to understand the early Noachian geologic record, to interpret it, to know what it can tell us about early Martian history, we have to know what degraded early Noachian landforms would look like today, and we have to know what percent of those landforms would be preserved. Because if we're only looking at the fractions of landforms that remain after 4 billion years of cratering and erosion, we're only getting a very small portion of the picture of what was really going on back then. So my advisor and I have developed a method to answer this question, which is what I'll be speaking about today. So first, we've written a model that simulates Martian cratering and erosion. We apply this model to topography for Martian landforms, and we use that to predict what certain types of landforms would look like today on the surface of Mars if they had formed during the early Noachian 4 billion years ago. We then search Mars's surface for landforms that resemble our model results, and these landforms are candidates for ancient features. And then, once we have all this information, we synthesize it to draw conclusions about what was going on back in the early Noachian. So the model that I've written is relatively simple, runs pretty fast, and it models the key processes that have shaped Martian history, which are impacts and erosion. The model is calibrated to recreate early Noachian terrain. Here I show an example of 4 billion year old fake terrain that I generated with my model compared to real early Noachian terrain. And you can see, obviously it's not a perfect match, but the craters have a similar size and there's a similar number of craters. When we apply this model to a landform, for example, this little volcano here, then the result for the model age that we choose shows us what that landform might look like if it had formed that many years ago. So this is a prediction of what this volcano would look like if it had formed 4.05 billion years ago. I have a little video here actually that shows my model running, starting with that volcano. Woo. So I think this does a good job of showing how much higher the impact rates were early in Martian history, because the video is still running, I believe, yes. But as you can see, it really slowed down with cratering after a few frames. So there was definitely an exponential drop of cratering, which is one of the reasons why early Noachian terrain is so much more heavily cratered than other parts of Mars. So we use various types of landforms as input for our models so we can see what different types of landforms would look like today. The three major types are volcanoes. I'm sure most of you are familiar with volcanoes, but they are openings in the crust of a planet where lava and gas can escape due to subsurface activity, and there are plenty of inactive volcanoes on Mars, so it's good to know how volcanoes evolve. We also look at tectonic landforms. This can be a bit confusing because on Earth, when you hear tectonic, you often think of tectonic plates. But Mars does not have tectonic plates, but it still has tectonic activity. In this case, tectonic activity just refers to the movement of the planet's crust, and landforms that form along fractures in the crust. So there's two major types of tectonism that I'll talk about here. We have compression, where the crust pushes it together, and extension, where the crust pulls apart. This is an example of a extensional tectonic landform on Mars. It is a rift valley called Tempe Fosse, and you can imagine that this type of landform would be created if there was a fracture right here, and then it was pulling apart at that fracture, creating a gap in the crust. And then the third and perhaps most interesting type of landform, depending who you ask, are fluvial landforms. We use valley networks, which are these systems of valleys that were common on Mars during the late Noachian and early Hesperian that were carved by ancient rivers of liquid water. And they're some of the most promising evidence that Mars once had water, because it's hard to really explain this type of thing without some type of liquid at least. And then, as I said, we are going to search the surface of Mars for landforms that look like my model results. I've spent many a tedious hour combing these study areas for potential ancient features. For volcanoes, we look at all of the early Noachian terrain on Mars, which is highlighted by the black, I don't know, calling them polygons might be a stretch. It's within the black regions, and then we do a finer search for tectonic and fluvial features in the purple squares. So let's get into some of my results. So we ran our model on 2 volcanoes. We have this huge volcano, which is one of those 3 Tharsis Montes. It's, as you can see, like over 10 kilometers tall. And then we have a smaller volcano, Biblis Patera, which is a little guy with a huge caldera in the middle. Both of these fare pretty well when we run the model with an early Noachian age. There's plenty of craters, and the shape definitely changes, but they still maintain elevation around the surrounding terrain. And if you were to see something like this on ancient Mars, you'd still probably recognize it as some type of mountain feature. And we did, in fact, see features like this on ancient Mars, quite a few. Here's some examples, and I was, if anything, pleasantly surprised by how well some of these resemble my model results. So we actually found about 80 candidate early Noachian volcanoes across the Martian surface, which, you know, maybe not all of these are volcanoes, but if at least most of them are, that would indicate that early Noachian volcanism was pretty widespread across the planet, which is an interesting thing to know when we're thinking about Mars' thermal evolution. But we still want to know how early Noachian volcanism compares to later rates of volcanism that formed the huge Tharsis volcanic province, which is right here. It's a little harder to see with this black and white map. So when we take the total volume of all of our potential ancient candidates and then estimate their original volume, we can estimate an ancient volcanic rate of about 14 cubic kilometers per 1,000 years, but the estimated rate that formed the Tharsis province is about 1,500 cubic kilometers per 1,000 years. So obviously, while there was probably a lot of volcanism in the early Noachian, it's nowhere near as much as there was later on. It's about 100 times less. So this indicates that there was a peak in volcanic activity around 3.7 billion years ago, which is interesting because a lot of models of Mars's evolution would suggest that there was just a steady decline in volcanism throughout time, but our research suggests this is not the case, and we might have to adjust some of our assumptions. Before we get into tectonics, I got another quiz trivia question for you guys. What are the 2 types of major tectonic feature that I mentioned before? Is it compressional and extensional, rift and ridge, brittle and ductile, or in and out? Anyone know? Yeah? It is A, compressional and extensional. The second 2 are sort of trick answers because they do have to do with tectonics. The 4th one is a burger chain, so it's not correct. So we ran our model on 3 different types of tectonic features. I showed you before the rift tempe fosse. We also have a lobate scarp, which is a type of compressional feature that forms when the crust pushes together. And then a wrinkle ridge, which is another type of compressional feature, but it's a lot smaller. The scarp and the ridge both remain recognizable when we run the early Noachian model, which indicates that we would still see these types of tectonic features on early Noachian terrain. The wrinkle ridge, however, is pretty much totally wiped out by these craters. I don't think anybody would look at this image and see tectonics, so we don't really expect to see a lot of wrinkle ridges still around. which is interesting because wrinkle ridges are a very common type of tectonic feature on Mars, and so if we're missing a lot of that from earlier on, that means we could be missing a lot of tectonic context from early Mars. And we do find also quite a few potential ancient tectonic features. This is an example of a candidate early Noachian rift that has been kind of widened and shallowed by erosion, like our model result, which I think is really cool. This is an example of a potential ancient lobate scarp, which resembles this model result. And this is a kind of iffy example of maybe an ancient wrinkle ridge, just to give an example of what that could look like, though I'm not totally confident in that one. And here I have mapped the tectonic features in those two focus study areas. The yellow features are compressional and purple are extensional. The blue are fluvial features, don't worry about those right now. I think it's interesting that these two regions, both of which are some of the oldest regions on Mars, are very different when it comes to how many tectonic features of each type there are. There's obviously a lot more extension happening in study area 1. A lot of these extensional features are actually parallel to the rim of the giant Hellas impact, which implies that they could be somehow associated with that impact structure. And it would make sense that they're early Noachian since the impact structure happened right at the beginning of the Noachian. And then we have a lot of compression going on in study area 2. There's a lot of compression in both, which kind of implies that compression is more of a global phenomenon, whereas extension might be more linked to specific processes like this giant impact. And last but not least, well, maybe least in some ways, fluvial features. They are least in the sense that they are probably the worst preserved out of these three types of features, which is a sad news for astrobiologists everywhere. They are pretty dramatically altered by impact cratering. Large trunk channels, like the main channel of this large valley network called Maud and Vallis, are fairly well preserved, though they kind of resemble extensional tectonic features when they're this heavily degraded. And the trunk channel from a mid-sized valley network like Muriel Vallis can be slightly preserved, but I don't know if one would recognize this if you didn't already know it was there. And then a more shallow branching valley network like this one here is pretty much completely wiped out by a combination of erosion diffusing the landscape and also cratering. So it seems like a lot of evidence of early Noachian valley networks would be wiped out if they had formed. Current consensus is that there wasn't valley network formation in the early Noachian because it's thought that the climate was too arid. But my results indicate that even if there were, we wouldn't really know because they would be so heavily cratered and degraded. So I don't really think that we can say conclusively that they were never there. I also think it's important to note that small streams and tributaries are erased by cratering and erosion even when the main channels are preserved. So we're losing a lot of detail in these types of features. We do find a few little candidates that resemble fragments of degraded valley networks. They're gonna appear more like disconnected troughs than like actual branching valley network features. So I think that if we're looking for valley networks, if we're looking for early Noachian valley networks that look like younger valley networks, we're kind of looking for the wrong thing. If these are parts of early Noachian valley networks, that would indicate possibly a more humid climate in the early Noachian than previously assumed, although this definitely isn't enough evidence to say anything like that conclusively. So, thank you all for bearing with me. I know I got into maybe a little bit of technical detail about my model and such, so I hope we are all still excited about Mars. To summarize what our results say about ancient Mars, I think the biggest thing is that the early Noachian geologic record is partially preserved, but it's incomplete. So when we look at really old terrain on Mars, we're only seeing part of the picture, and if we're gonna make any conclusions about what was happening in the early Noachian, we have to account for the fraction of the geologic record that has been lost to craters and erosion and whatever processes were going on. There's evidence of widespread early Noachian volcanism, but not on the scale of later eruptions that were forming things like the largest volcano in the solar system. There's evidence of both compressional and extensional tectonics in the early Noachian, which has implications for some complicated thermal evolution stuff that I won't get into. And unfortunately, it seems like if early Noachian valley networks or other types of insides fluvial features existed back then, they're probably gone, but this is an interesting result because it means that the common assumption that there was no valley networks forming back then is possibly incorrect, just because I don't think that we would know if they were. So now we can revisit that Martian timeline from before, if y'all remember. But we can fill in a little bit about the early Noachian. We know that there was widespread erosion of craters, but minimal, if any, valley networks. We know that there was moderate but spatially widespread volcanism across the planet, and we know that there was both compressional and extensional tectonic activity occurring, some of it possibly associated with this giant Hellas impact. And obviously there's a lot to learn still, but we're starting to fill in some of these details about the early Noachian, which I think is very exciting. So what next? I still feel like I have a lot of work to do on my Martian journey. There's a lot of unanswered questions. I want to know things like how much water was present in the early Noachian. Were there valley networks forming? Was that something that could have been possible under those climate conditions? Or would they just have been wiped out by craters so fast that they couldn't even have time to really form? I also have, as I mentioned before, a lot of questions about this mysterious pre-Noachian period. That was actually going to be the original focus of this research project, but then we realized that the method we were using with cratering landforms didn't really work because there isn't any terrain on Mars that dates back to the pre-Noachian, so we couldn't really model something that doesn't exist. But we're trying to formulate some ways to look into that mysterious period. So overall, if you take away anything from my talk, it's that Mars, while very interesting today, has also been through a lot of different phases, like we all have. And I think it's very exciting to piece together the past and understand more about what was happening, and if there could have possibly been habitable environments, or if it was just a mess of craters and volcanoes. So I thank you all for listening, and I'm happy to take any questions that you have.
In the back over here.
Yeah.
To what extent did any of the rovers capture any of the areas you identified as Noachian? And if they didn't and could, who would you choose first?
You asked if any of the rovers have identified places as...
Visited any of the places you identified?
You mean like the places I ran my model on, or...
Yeah, that the model indicated this is early Noachian terrain.
So, my model was more like showing how things would look if... Oh, I see. Sorry, I misunderstood the question. Are you asking if it visited any of the like features that I identified as early Noachian? That's a great question. Honestly, off the top of my head, I don't know, but that's definitely something I should look into. I know that the rovers have looked at like really old material on Mars. I think that Perseverance has been looking at some crust that's been like excavated by the Isidis impact, which is another big impact during the Noachian. It's been looking at some materials that are early Noachian or maybe even pre-Noachian. So that's been exciting to see some more information from the like geochemistry side of things. But I wish I had a more detailed answer, but I encourage anybody to look up like what the rovers have found about the early Noachian. Thank you. Any other questions? Yeah?
Yeah, so how are you dating the time periods anyway? Is it some kind of radiometric dating on the ground surface, or how
Are you talking
Yeah,
about like for the timeline?
Yeah, I mean, I know what the timeline is, but is it like, are there radiometric dates from the ground that say it's 4.8 million versus some other kind? And then the stuff you're testing against, you have some kind of basis to say that stuff is.
Yeah, so your question is how do we tell how old certain parts of Mars are, and how we define the ages of the different geologic boundaries, and
No, it's the you using radiometric dating or some other kind of dating for figuring out.
So that's a great question. One of the reasons that we want to do Mars sample return is so that we can do radiometric dating like that. We haven't been able to do any actual absolute dating of Martian material. So any absolute date ages that I was talking about are subject of debate. How we estimate ages on Mars is by looking at how many craters there are in a certain region, because we assume that older surfaces have had more time to get cratered, and so will have more craters. And there are a lot of people who have studied, but very closely studied, impact rates in the early solar system, and a lot of this is sort of based on what we see on the moon, because the moon hasn't undergone as many erosional processes as Mars. But there's people that have kind of set up these chronologies based on the density of craters in an area, where you can look at a certain area and say, okay, well, there's this many craters which aligns with this age. And so terrain that we define as Noachian corresponds to a certain density of craters, and so does Hesperian and Amazonian. And I think that the way we define the geologic boundaries on Mars is more relative than absolute. So if a surface has less craters than another surface, we know it's younger.
Yeah.
We can't be extremely certain that a surface that we've said is 4 billion years old is exactly that. It's sort of our best estimate based on the crater density. But if we're ever able to bring back samples from Mars and do that type of radiometric dating, we would get much more definitive answers on how old things are. Did that answer your question?
Good answer. I like that. I'm a geology background. I don't understand a lot of this.
Cool. Well, I'm glad that answered your question. Anybody else? Right. Thanks, everybody.
Let's thank Ruby one more time.
Hi, thank you once again, Ruby. Let me pull up my notes here for when our next show will be, but it will be at 7:30 right here at same time, same place on May 20th. So we hope you've enjoyed our show tonight. Please come back on May 20th for our next show. Don't forget to tip your bartender and close your tabs. Our 2 trivia answers, please come visit us real quickly at the back to get your free piece of merch. And with that, thank you all for coming once again. We will see you back here on May 20th for Space Drafts 117. Thanks so much.